avoid aliasing by high resolution signals. Yeah. High resolution signals, and usually large in applications. Yeah. So now you need to expect, we use large n numbers, because resolution is very important. Okay, all right. Computation efficiency. Now we need to look at this computation efficiency question. Yeah. So this is a computer algorithm concept. Here I need to use some computer algorithm terminologies here. Okay, a little bit, not too much. Yeah. This efficiency issue. All right, yeah. For each component, when we calculate each component Fourier coefficient, so this is the formula. Yeah. All right. Yeah. XK, that's our notation. Yeah. All right. Then, how many multiplication? This big O notation. That's a computer algorithms. Computer algorithms terminology. Okay, big O notation. Yeah, here, let me give you a short description, because we cannot spend a lot of time learning knowledge in computer algorithms. Okay, yeah. Here, because this big O notation we call the asymptotic notations in computer algorithms. Asymptotic notations. Notations. Yeah. All right. This big O, because we want to use short notations to represent some special meaning here. Yeah. This big O of n represent a class of functions. Yeah. A class. Yeah. Many functions. So a class of functions. Of functions with the property, so with the special property. What's the property? Yeah. All right. So the function, that f function, so when you calculate that function, okay, calculate that function, let's say n, because that function related to the data size n, okay, related to the data size n, can be bounded by c constant, some constant, c constant times capital N. Okay, the computation you need to use to calculate this function. Okay, or you apply this algorithm. Okay. Yeah, because you have algorithm, right? When you calculate this number, you use this formula. This formula you treat it as your algorithm. This is your algorithm. Yeah. But when you apply this algorithm, how many multiplications do you need? Right? Yeah. The multiplication here, look at the number of multiplication, you need n multiplications, right? N multiplications. N multiplications, so you choose c equals 1. How about that? Yeah, 1 times n. So that's why we say it is a big O of n, the number of multiplications. Yeah. So that constant is 1 times n. Yeah. Bounded by constant c times n, number of multiplications, when you calculate this formula. Okay? All right, so that's the meaning here. All right. For n components, but you have n components, right? When you do one coefficient calculation, you need n multiplications, but you need to do n. So you need to multiply another n. N times n. So you you need n squared. So to calculate the whole vector, how many multiplications do you need? The whole vector. Big O of n squared multiplications. Big O, that constant C here, it's 1. Okay? Yeah. So the multiplications you need, you know the algorithm, right? Calculate. Yeah. The C. You know, algorithm. So here we're talking about the algorithm to calculate this coefficient vector bounded by C. Your C is 1 times n squared. That's the meaning of big O of n squared in computer algorithm terminology. Okay? Yeah. That is slow. Yeah, n squared. Why? This number is too big and the total calculation too, because n is a large number. The capital N in our real world applications, usually it is a large number. So the large number, you take n squared, even larger. Too large. Okay? So you want to reduce this efficiency. Here we call, so this big O notation, we call it efficiency. Yeah. So you want to improve the efficiency of this algorithm as much as you can. Yeah. All right, so let's do the improvement. Yeah. When n equals 1,000, n squared 1 million. Okay? So when you need to process data with 1,000 sampling values, you need to do 1 million multiplication. But that is just one Fourier transform, one discrete Fourier transform. But usually you need to do many discrete Fourier transforms. Yeah. So then you need, because the time cost very high. So you want to significantly reduce the time cost here. All right. How to make the computation faster? So our next question, how to make the computation faster? How do we take advantage of the structure of the Fourier matrix? Now, the structure very special. Can we explore its structure properties such that we can take advantage, use that special structure to make our computation much faster? That's the next question. Fast Fourier transform answers this question. Yeah. All right. Fast Fourier transform. All right. Improvement. Yeah. All right. The improvement. Let me give you the final result first. Yeah. Before we work on the details of the algorithm. The fast improvement is from n squared to n log n, log base 2 of n. That's the improvement. Okay? Yeah. N squared to big O of n log base 2 of n. Right? That improvement is quite a lot, quite significant. Yeah. How can you see it? Yeah. How do you know this improvement is very big? Yeah. How can you see that? Yeah. Here I like to use some numbers to let you know why this improvement is so big. Okay? Yeah. You need to plug in some numbers to see how many times is the improvement, right? Yeah. You want to see that big improvement. How many times is the improvement? 100 to 1 improvement, is that good? 100 to 1 improvement, is that a good improvement? Yeah. Suppose the old way you use 100 time units, but with this fast Fourier transform, you just use 1 time unit. Is that big improvement? 100 to 1 ratio. Okay? Yeah. But actually, even bigger than that. Okay, here 100, I just give you an example. All right, let's look at the, so calculate improvement factor when n equals 1,000. Okay, all right. Then let's take the ratio. N squared over n log base 2 of n. After cancellation, n over log base 2 of n. Okay? And this time, you can see, yeah, the improvement is approximately 100. 100 to 1 ratio, right? Yeah? Yeah. So when your data size is 1,000, 1,000 is not a large number, right? Yeah. 1,000, yeah. You know, it's not a very big number. Even for 1,000, this data size, you can improve 100 to 1 ratio. That's significant. That's significant. Yeah. The larger the n, your improvement ratio is larger. Yeah. The larger the n, your improvement ratio is larger. All right. Let's look at the 1 million. When n equals to 1 million, but this time you need to calculate the ratio. That ratio is 50,000. That improvement, huge, right? Yeah. When you apply the fast Fourier transform, the time you need is 1/50,000th of the original time. How big it is. Suppose T0. T0 is the original time. If you do not apply fast Fourier transform, okay, you just apply straightforward, discrete Fourier transform multiplication. Then you need a T0 time, okay? But when you apply fast Fourier transform, the time you need 50,000th, okay? 1/50,000. That's huge. That's huge improvement. Yeah. So that's why this algorithm is so important. Yeah. In a real world application, so important. Yeah. All right. Next, we want to see how to do it. Okay. The details. How to do the fast Fourier transform. How can we get this fast? Okay. Yeah. So I explained the main idea. Yeah. All right. E.2, fast Fourier transform. Property of computation efficiency. Yeah. All right. When there are even number of samples here, what property we want to use to improve the efficiency? Yeah. Yeah. So the property, we consider the special case, not the general case. Fast Fourier transform. We want to use some special structure. All right. Even number of samples. Yeah. For all number of samples, we cannot use fast Fourier transform directly. Yeah. But in the real world, when we have odd number of samples, we need to add one more sample to make it even. Okay? Yeah. Add one more zero to make it even. Then we can do fast Fourier transform. Yeah. We need to find some approximate way to allow us to do fast Fourier transform. But in our discussion, we assume there are even number of samples. Even then we can split one half, first half, and the second half. Other we cannot split in that way. Okay, so we need an even number of samples, first half and the second half. Yeah. All right, n equals 2n. Yeah. Then this Wn. The basic structure for the Fourier matrix, or we can call the basic element, yeah, just some basic number we need to use to make the entries of the Fourier matrix. Yeah. All right, but we also need, because we also need to make another related matrix we use this Wm. Yeah. Wm we define similarly, yeah, because we will use a different matrix in our calculation. So we define the Wm. Yeah. Then you can see Wn squared equals Wm. Yeah, that relationship. All right. And xk. Yeah. Then let's look at the discrete Fourier transform by the usual formula. Yeah. All right. Yeah. Here you can see when we calculate the summation, the k value can take even and odd, two different cases. Yeah. Now we split these two different cases. We split. Yeah. Even case, even term, the coefficients for even terms, we group them together, and the coefficients for the odd terms, we group them together. So we have two groups. Why? Because when we do this kind of grouping, yeah, these two groups have some similarity. Now we want to explore the similarity. Why you explore the similarity? Because after we discover some similarity, then we can reduce the computation redundancy. Yeah. Yeah. We reduce the redundancy of the computation based on the similarity structure. Okay? All right. Yeah, you will see that soon. Yeah. Signal, original signal, like this. Okay? All right. Then we split the signal into two halves, even half and odd half. Even samples, odd samples. All right? Yeah? Two vectors. Yeah. Yes. Even, odd vectors. Same size. Yeah. All right. Then, first let me give you the formula of the fast Fourier transform. Yeah. After that, then we understand why we can use this formula. Okay? First, just give you the fast Fourier transform operation directly. Yeah. Yeah. Then we understand why is this. Yeah. All right. Then, yeah, to do the fast Fourier transform, we use a smaller size Fourier matrix. F sub capital M in this way, because F capital N, that is our original Fourier matrix, right? Yeah, this is original Fourier matrix. Now you can see the number of entries in this matrix. You compare with that, 1/4, right? 1/4. Yeah? Because the number of rows you cut at 1/2. Number of columns you cut at 1/2. 1/2 times 1/2, 1/4. Okay? Yeah. So the size of this matrix, if you look at the entries, yeah, if we look at this is the original matrix, okay? This is the Fn original. There, horizontally, vertically, you divide half. That matrix is just the data in that matrix much smaller, like that. Okay, 1/4 of the numbers in that smaller matrix. Now, in our fast Fourier transform, we will use this smaller matrix to do multiplications. All right. Then, the first operation, we do matrix multiplication. Capital Fm times that even part of the sampling values. Then the second one, F odd, yeah, transform, yeah, Fm times the odd sampling values. Yeah. All right, and these two vectors, yeah, we use them as the intermediate vectors. Okay, yeah. So these two, so not the final. Yeah. So they are the intermediate vectors. Yeah. The stepstones we use to get our final Fourier coefficients. Yeah. All right, after that, we need to do the next level. How to get the final Fourier coefficients? Two parts. First half, second half. Yeah, because first half, that n from 0 through capital N minus 1, that's the first half. Okay. The second half, n plus capital M, second half. First half, we use these two intermediate vectors, but this W, this we defined before, right? Yeah, we defined before, times that vector. Okay. Second one, the vector multiplication, that one. Yeah. So in this way, so this, if we implement, calculate these coefficients, we call this is the fast Fourier transform. We do it this way, fast Fourier transform. Okay. Then I will explain. Why this is fast Fourier. Why it is fast. First, why these formulas give us the same transform result. First, we need to understand that, right? This formula, in this special form, what do we get? The same as we get from capital Fn is F vector, right? Yeah. So same result. That's the first. Second, after we see they are the same, we also need to know why they are faster. Okay? Why this way they use capital N log base 2 of n. This many multiplications. Yeah. If we answer these two questions, then we complete the understanding. Okay? We complete understanding of the fast Fourier transform. Yeah. All right. Yeah. Now, yeah. So I put these formulas aside. Yeah. So now we need to understand. First, we understand the correctness. Yeah. The formula, the result is correct. If we calculate in this special way, we get the same results. Yeah. All right. Let's write one typical Fourier coefficient. Okay, one typical. Yeah. So the first time we write them out explicitly. Yeah. All the terms out explicitly. Yeah. Then even terms, odd terms, we separate. Yeah. We group all the even terms, all the odd terms. Yeah. Then the first group, even terms. Second group's odd terms. Yeah. Okay? But you can see the odd terms after we factor out this W, M, capital N, and N. Yeah. Inside, that is the structure. Okay? So you compare these two structures. Yeah. The W part, the same, right? The W part is the same. Yeah. Yeah. The difference is we change from even samples to odd samples. Okay? Even samples to odd samples. Sampling values. That difference. Yeah. The W part is same. Can we use that? Can we use that capital Fm matrix multiplication? Yeah. So that's the reason we use capital Mn matrix. Yeah. All right. Because here you can see that the exponent is even number, right? The exponent even number. Exponent all even numbers. Even number, we take that 2 out. There we get, because look at this. W capital N square equals Wn. So we can change to, Wm representation. Okay? All right. Wm representation, that's we use to form Fn matrix. All right. Fn matrix multiplication. All right. Yeah. So when n greater or equal to W, that's the second half. Yeah, first half, second half. Yeah. Yeah. All right. Huh? Yeah. Oh, good question. Oh, that should be n, not m. Yeah. Okay. Yeah. Good. Yeah, good. This is wrong. This should be n. Because our f part, we do not change anything. Yeah. Our f part, yeah, so here, n minus 1. We do not change the, subscripts of f things. Yeah. F sampling value, we should use the original sampling values. Yeah. Okay? Yeah, good. Yeah, so typo, I didn't notice that. Yeah. All right. Yeah. Good. Yeah. So then for m greater or equal to m, that's the second half. Second half, let's take one m out. So this m in the first half. First half, this is the first half. Okay, yeah. All right. Yeah, so then let's calculate that. Yeah, all right. Calculate that. Yeah. All right, for the second half this time. Second half, we can take this part out, but this number is -1. Okay? This one number, yeah, because that number, look at this number. This number is -1. E to the negative pi I, that's -1. That's why when we calculate that, we only need to change the sign. Yeah. So for the second half, we do not need to do another round. Let's just change the sign. Yeah. So that's why our intermediate, when we calculate two intermediate vectors, the second half, we only change sign. Yeah. Yeah. All right. Yeah. So now, yeah, look at that. The first half, we add that. Second half, we only need to change the sign. Okay? Yeah. That calculation. Yeah. Here, when we do the calculation, now this time I need to discuss the efficiency part. Efficiency part. Now, this time we need to count the number of multiplications we need to use. The goal, calculate this vector by removing the redundancy. Okay? Yeah. Because in the original algorithm, there is a lot of redundancy. Yeah. So now we apply this fast Fourier transform. The basic idea is we want to remove the redundancy. Yeah. Now I want to show you how to remove the redundancy. Yeah. First, we split into two halves, the first half and the second half. Yeah. All right. Then the first half can be represented as the sum of these two vectors. Yeah. The second half represents some subtraction of these two vectors. Yeah. All right. But the subtraction, when you do subtraction, you need to multiply this, WMN, yeah, to the second intermediate vector. Yeah. All right. So here we use the idea, reuse the resource. In computer algorithms, one basic idea that we use to improve algorithms, that's to reuse the resource. Now, what's the resource? Your computation results, your intermediate computation, these two vectors, your intermediate computation results, that's your resource. Yeah. Because you need to spend time. You need to spend your precious time to calculate the intermediate results. So that intermediate, you should reuse them as much as you can. Yeah. All right, so here, the first time we do, yeah, all right. So we do this calculation, okay, all right. So here, we need to calculate intermediate results. Then, one number, you multiply the second intermediate vector. Yeah, all right. But, look at that, this. When you calculate this one, you do addition of two vectors. But when you calculate the second half, you do subtraction of the two vectors. That means for the second half, you do not do any new multiplication, right? Yeah. So first half, you do multiplications in this vector, that vector, and this multiplication. But you store the result in a temporary variable. Temporary variable. Okay? But the second time when do subtraction, you just retrieve the temporary variable, you do subtraction, so you do not have any new multiplication. That's safe. Yeah. Second half, no new multiplication, you just do subtraction directly. Okay? Yeah. All right. Yeah. Then, so let's look at the number of multiplications. This time, we calculate the number of multiplications. Yeah. We use a function, capital H of m, as the number of multiplications to calculate this f vector, f hat vector. Yeah. So we need to estimate this number. How large is this number? Using the fast Fourier transform. All right. All right. To calculate, yeah. First, we need to calculate that matrix, Fm times Fem. Yeah. So to calculate that, we use H of m because it has when we calculate this matrix multiplication, this matrix, oh, yeah, why? Oh, something strange. Yeah. This multiplication, it has the same structure as our original multiplication. Same structure, right? If the same structure, can we apply fast Fourier transform recursively to calculate? Recursively. Okay? Yeah. So the number of multiplication we need, capital H of m multiplication. All right. Then to calculate the second vector, yeah, so that's just like capital M times that, how many multiplication? So m multiplications inside, yeah, because each component we need to do multiplication. M multiplication inside, then plus we do another fast Fourier transform. That's capital H of m plus m. Okay? That means we have a recurrence relation. Capital of n equals 2 times capital H of m plus m. That's our recurrence relation. Yeah. And we have base cases. The base case, capital H of 2, where you have two numbers. Okay? The smallest vector, two numbers, you need one multiplication. Yeah. Yeah, because you split in the middle. Yeah, so there you do multiplication. But the multiplication, your addition, subtraction, yeah. So you do one multiplication. All right. Now, let us solve the recurrence relation. Yeah, this is a recurrence relation we need to solve. Okay? Yeah. Solving this recurrence relation, yeah. Here, I use capital N equals a power of 2. 2 to the pth power. Power of 2. And to see what is the result. Yeah. Yeah. So the remaining, I just plug in to do the calculation a little bit. Yeah. All right. I do some transformation. Yeah. In that way. So after the transformation, yeah. So you can see, yeah. we can do iterations. Keep doing iterations. Yeah. Then you can see, at the last iteration will give us this number. Yeah. All right. So that number, then P over 2. Yeah. So we get a H. So we get that number, n log n. Yeah. H to this capital N. Yeah. So where n is a power of 2 numbers, so we get 1/2 n times log base 2 of n. Yeah. Yeah. So in this way, you can see, yeah, that's the reason this algorithm is this fast. Yeah. N log n. Yeah. N log n. Efficiency. Yeah. So we call it efficiency or complexity. Yeah. Efficiency, complexity. Yeah. Yeah. Or performance. Yeah. Yeah. So the current terminology people use efficiency. Yeah. Old way people call it, performance or complexity. Yeah. Yeah. All right. So now, we complete 2 things. First, formula is correct. Yeah. Fast Fourier transform. Yeah. We use a different way to calculate the Fourier coefficients, but we get the same result. The first thing. Second, why this new algorithm is faster than the old one? We find that recurrence relation. And we solve this recurrence relation. We can see the number of multiplications we need is this many. Okay? That many. Yeah. That's a huge improvement. Yeah. Yeah. When we use the concrete numbers, remember where n is 1 million, that huge, large number, your improvement is 1 over 50,000. 500,000, okay? 1 over 500,000. Oh, not 500,000, 50,000, not 500,000, 500,000, okay? 50,000, 1 over 50,000. Huge, that ratio is, huge improvement. Yeah, with a huge improvement. Yeah. All right. So the questions for this topic, I give you in the concept questions. Okay, yeah. Our part A of the final concept questions. So I give you, 2 or 3, yeah, 2 or 3 such questions, yeah, about fast Fourier transform. Okay, yeah. So make sure you understand. You have some basic understanding. 2 or 3 concept questions, but no computation questions. Yeah. All right, that's it. So let me stop right here. Yeah.